Okay, so next one is the one proportion z-test. You can see in this problem 7 here that I have a random sample of 200, 140 of which said they have well, I can't even write 140. 140 of which said they had a computer where they reside. They either have it or they don't. So this is a qualitative variable. And so the proportion is just going to be x out of n, or 140 out of 200, or 0.7. In other words, 70% of them have a computer where they reside. So for part A, it says to construct a confidence interval for that. I'm going to do that right over here. P hat plus or minus z, the statistic plus or minus the confidence coefficient, times the standard error, P hat Q hat over n. So we're going to have 0.7 plus or minus, and for 90% that's 1.645. This is just using the z table like exam 2, times the standard error, which is going to be the square root of 0.3 over 200. So I'm just going to do on my calculator 0.7 minus 1.645 times square root of 0.7 times 0.3 divided by 200. Close my parenthesis. And I've got 0.647. That's 646695. So that's subtracting. So I'm going to do the same thing, but this time I'm going to add the margin of error, 0.753. So that is our 90% confidence interval. Statistic plus or minus confidence coefficient times standard error. Okay, the sample size problem and assumptions and all of that, really B and E, I'm getting at the same thing. Do we have a large enough sample? Here's where things get, I don't know, not tricky necessarily, but you just have to remember this. This is a qualitative variable. Nothing to do with the 15, 40, 100 rule. You may remember, hopefully recall what we did with the binomial distribution, that as we either increased n or got closer to 0.5, we had a large enough sample for a bell curve. I'm actually, I think, going to make it maybe a little easier than that. As long as you recognize it's a qualitative variable, what you have to know is that the number of yes has to be greater than 5. The number the number of no has to be greater than 5. So both of those have to occur. So what do we have? In our sample, the number of yes was 140. 140 out of the 200 indicated they had a computer. That means that the number of no had to be 60, or just 200 minus 140. Both are greater than 5. N is large enough. No assumptions other than that you have a random sample, which it already says here, are required. We have a random sample, and our sample size is large enough. So that really takes care of B and E. I don't know why I wrote both of them on there. So part C, we have a hypothesis test. And we want to know if we can conclude that there is a difference between the population, if the population proportion is different from or not equal to 0.75. Means we're going to have a two-tailed test. And it means that would have been nice if I had had a 95% confidence interval. But we go with what we've got here. That doesn't necessarily have to be true. It just would have been nice. So we're going to reject HO if z-test is greater than 1.96 or less than minus 1.96. And you have that table in your set of tables that from the last test for the z-values. Also, if you have your t-table, if you would look on the second page at the very bottom, the bottom row of numbers there where I have z, I didn't get it lined up right, but where I have z and you've got n is equal to infinity. By the way, those are, as n approaches infinity, the t distribution approximates the z. So you could see that row of numbers there is 1645, 196, 2.326, 2.576, and then with your various confidence levels and 1 and 2 tests. So instead of looking on a separate table, you can find those z-values at the bottom of the t-table if you'd like. You can look in either place. But anyway, our test statistic is going to equal the statistic minus the hypothesized parameter over the standard error for this. Now, this is a little bit of an ouch here, but just the way it is. When we did our confidence interval, the only estimate for the proportion we had was what we had in our sample. But when we're doing this hypothesis test, and when we're doing the test and looking up our p-values and all that kind of stuff, it's based on the assumption that HO is true. So, when you're doing a hypothesis test, instead of basing the standard error on p hat, you base it on pH. So we're going to have pH QH over N. So our sample proportion was 0.7 minus 0.75. That was our hypothesized proportion over the square root of 0.75. That's the hypothesized proportion right here, times 0.25 divided by our sample size of 200. And I get minus 1.63, which is not greater than 1.96, and it's not less than minus 1.96. So I fail to reject HO. Mu could be 0.75. I'm sorry, P could be 0.75. By the way, our confidence interval here, which I really wish I'd made 95%, but that's okay. It's still consistent here. The population proportion could be 0.75 because the interval includes 0.75. The only reason I said I wish I'd made it 95 is that if you use a 90% confidence interval here and a two-tailed 05 test, you won't always have the exact same conclusion. You almost always will, but you would not be guaranteed to have the same conclusion with your confidence interval and your critical value. Well, now since this is a z-test, we've got this minus 163. We can compute our own p-value. Remember, always put the statistic here on the axis. Always put what you have in your hypothesis right here. Then the sample proportion we got was 0.7 in this particular sample. And then the p-value would be the area that was below z of equal minus 1.63. It's the same z we had here. And I have a z-table here. Well, I know I do. I just have to find it. So for minus 1.63, .0516. So we would reject HO. If p-value were less than 0.05, the p-value was equal to 0.0516, which is greater than 0.05 or not less than 0.05. Could have just put greater than, but either way, not less than 0.05, so we fail to reject HO. And you should recognize that this is pretty darn close. It's not less than 0.05, but it's pretty close to 0.05. That's one of the advantages of making a full statement, or certainly having a full understanding of the p-value. So we're saying if p is equal to 0.75, then there is a 0.0513 chance of getting a sample proportion less than or equal to 0.7. Now, if you use just the exact cutoff of 0.05, then dang it. Hopefully you guys could tell what I did wrong here. And that is that the p-value is not 0.0516. The p-value on a two-tailed test, we have to go the other direction as well. And there's another 0.0516 out here. And so our real p-value is going to be 0.1032. And so this is also going to be 0.1032. So if p is equal to 0.75, then there is a 0.1032 chance of getting p-value less than or equal to 0.7, or, I'm sorry, of getting a p-hat less than or equal to 0.7, or getting a p-hat greater than or equal to 0.8. And that's because it said different from here. Two-tailed test.